weekend, this weekend, next weekend.
This is Jamboree.
Yeah. Next weekend, guys, is the Jamboree. Not this weekend, but next weekend. So the Jamboree is the annual combined lapidary clubs event, the Australia-wide event. So we've got dealers from all over Australia coming down. It's at Ballarat at the Federation University campus. It's about 2 hours out of Melbourne, but it'll be well worth it if you've got some spare time. Maybe want to take the family up to look at rocks. It's always on Easter long weekend. So don't forget about the Jamboree if you have the opportunity to head on out. Also, this Thursday we have the tutorial. So the timetable, you look quizzical look.
Hey?
Yes. Sorry, you're just like, what?
Yeah.
Sorry, I was just like teasing you because you're like a little meerkat that like eating going, ooh. So this Thursday is the tutorial for tutorial number 2 for crystallography. The timetable says that is going to be online, which was what I was anticipating. But after the first tutorial where a number of people wanted to be in person, we can run one of the tutorials in person and one of the tutorials online. This time round, we've got David, Adele, Dorothy, and myself. And as a bonus, there is no National Council of Jewellery Valuers talk on that night, but there is a committee meeting, which is easier for me to get up and walk out of at 7:30. For those who remember what happened to the first tutorial. So we'll be dividing you guys into 4 groups. But 2 groups will be online, 2 groups in person. Adele, are you happy to do an online from home, or would you
to do it in person?
You prefer to be in person? Okay, so
Then I can check you all right.
So Dorothy and I are going to be on site because we've got the management committee meeting. Adele will be on site. David will actually be on site because we've got the management committee meeting, but he'll go off to his office to do the online. No, that's on heater because we were cold. Are you hot now?
Yeah.
Okay. We might do.
We're not going to say take it off when you say that.
It was a little bit chilly when we walked in tonight, and I just want to take the edge off the breeze, of the air. So I'll send out an email tonight, just to canvass who wants to be in person and who wants to be online, and then we'll send out the meeting codes for the online tutorials.
When I know who's in my group, I'll probably send you another email. I hope that everybody's actually done their work. I see some not, I see some absolutely. Get down. Down the back. I'm hoping everybody's had got a workbook because I like people to actually hand stuff into me, to email me, and I will give you feedback. Okay, but that means that I need at least a bit of time to go through the work if I'm going to do you justice. So I'm hoping that you've really got your workbook under control.
So email it to.
If you're in my group, you might not be lucky.
You know who's group? How do you know who's group for me?
I don't know yet. We'll sort that out.
Because we that first tutorial, David was sick and Adele was away, so it was we weren't doing proper tutorials. So this time we will divide you into 4, but because it's the last of the online ones, it just depends on who wants to be online and who wants to be in person. We may switch you around into different groups again for the tutorial 3. Well, it just depends. It depends on how many people want to be online and how many people are in person.
How many people can actually come in on Thursday?
Yeah.
Okay, so Thursday's a little bit.
Yeah.
The regular beat.
So that's
So
why.
that doesn't look like a huge amount. Can I see hands again?
Wait, what's this for? You coming in? For coming in?
For tutorial on Thursday, okay, thanks.
Yeah.
So that's really one group.
Yeah. So we'll see how it
Okay, well, we'll
everything
discuss
pans out.
Yeah.
Yeah. Okay, so tonight's PowerPoint, I've only just uploaded to Moodle in the last 10 minutes. So for those of you at home sitting on the computer, you can access the presentation. For those of you in class, if you have a laptop in front of you, you can watch the screen as well. But otherwise, yeah, so sorry that didn't get uploaded until about 10 minutes ago. Tonight's lecture is the first of 5 lectures that we're starting on optics, on starting to learn about how light interacts with gemstones. And we'll be building up into how to use the polariscope and how to use the refractometer. Before we get to the polariscope and the refractometer, though, we have to cover some of the basics of how light works and how light interacts with solid surfaces. So tonight's lecture, Optical Properties Part 1, we're going to be going through the nature of light. We're going to be discussing concepts such as wavelength, the electromagnetic spectrum. We're going to be looking at reflection and refraction. So reflection is how light bounces off the surface of a gemstone. Refraction is what happens when light enters into the gemstone. And we need to understand the laws about how light is going to behave as it either reflects from the surface or moves into the gemstone. After we've talked about refraction, we're going to take it one step further and talk about something called total internal reflection of light. This has really big implications for us in gemology because of the way that gemstones are cut. They're cut to capture the light and to force it to reflect internally off the pavilion facets and then redirect that light back through the crown to our eyes. So a well-performing stone is cut because of principles of total internal reflection and also using something called the critical angle for the gemstone material. The critical angle is also related to the refractive index of the material also. So all of these theories kind of come together into helping us to understand how gemstones are cut and how they perform when they're being viewed in light. So we're going to talk a little bit tonight about understanding how gemstones are faceted. We're just going to talk briefly on it. I want to introduce concepts such as a well-performing gemstone, or what happens if a gemstone is too shallow or too deep, and what's actually happening with the light in those situations. I've got on here dispersion of light also. I'm not sure if dispersion of light is on this PowerPoint or the next one. Every year I kind of change around the order of my PowerPoints. It is on this one? Yay, excellent. We'll be doing dispersion of light at the end of this PowerPoint. Then we'll go on next week, start discussing refractive index in gemstones, defining refractive index. Then we come back to look at polarization of light and then go on to look at how we use the refractometer. So we've got 8 classes on optics. What we want to achieve after tonight's lesson is have a basic understanding of the visible colour spectrum. So we're going to be talking about wavelengths of light and which colours have which wavelengths and what the limit of the human eye is in terms of the colour that we're able to see. We're going to discuss the laws of reflection and refraction, and we're going to explain what total internal reflection is. Really, really important concept, not only because it underpins how gemstones are faceted, but also because the principles of total internal reflection of light underpins the operation of the refractometer. So when we come to discuss and learn how to use the refractometer, The refractometer works on the principles of total internal reflection of light. We're going to be defining what the critical angle of a gemstone material is, and we're going to be explaining in a little bit more detail what dispersion of white light is. Dispersion is one of those concepts that we've introduced to you already when we've been looking at hand lens, and hopefully everyone in class now has had an opportunity to look at something like a moissanite or a sphene or maybe a zircon or cubic zirconia that has a large amount of dispersion, and you might be able to recognize some of those tiny little rainbow flashes within the stone. We'll go into a little bit more detail tonight about what is causing dispersion and how we define dispersion. Then we're going to talk about how gemstones are cut and talk about things like windows and fisheyes and the performance of a gemstone material. Let's go over this. So let's start about looking at what is light. What we've got here on the screen is lots of different types of energy that form part of the electromagnetic spectrum. What our eyes see is a very, very, very small portion of that spectrum. Question?
Oh no, it was just dust in the air.
Oh, dust. Okay, no problem. So we have things like X-rays, and we have radio waves, infrared rays, ultraviolet rays, which are all part of the same type of energy, but that our eyes can't interpret. We're blind essentially to those portions of the energy scale. What our eye can see is a very, very small portion of that scale, and our eye interprets colors from a wavelength of 400 nanometers to 700 nanometers. And that's what our eye can see. Now, it's arbitrarily divided up into 7 colors, which includes red, orange, yellow, green, blue, violet, and indigo. And everyone's eyesight is just slightly different. So some people might be able to see more of the red and more of the indigo violet than others. But we'll talk about that a little bit later as well. So the visible portion of the electromagnetic radiation is what is visible to the human eye, and it's what's responsible for our sense of color of all the materials that are around us. We do need to know what the nanometer range of the visible spectrum is. And a nanometer is a way of measuring the wavelength of a particular wave function. 1 nanometer is actually equal to 10 to the minus 9 meters, which means it's 0.000000001 of a meter for every wavelength, or for every nanometer. So they're incredibly small. But nanometer is a unit of measure similar to meters or centimeters. We can convert between the two by using this little rule that 1 nanometer equals 10 to the minus 9 meters. Frequency of the visible spectrum, there's mathematical formulas that relate the speed of light, the wavelength, and the frequency to each other. The frequency we don't worry so much about when we're learning about color and light within gemstones, but we can work out or look up what the frequency of the visible spectrum is. The frequency of the visible spectrum ranges from 405 terahertz to 790 terahertz.
Do we need to remember that?
No, don't need to remember what the frequency is. In fact, for wavelengths of light, for the visible spectrum, yeah, I'll get onto that in a minute. It gets a little bit complicated when we start looking at what the frequency might be. But looking at the maths of it, the frequency of a wavelength of light or an individual color, frequency equals the speed of light divided by the wavelength of the light. So that's the mathematical formula. For those who've done a little bit of maths at high school and feel a little bit comfortable with transposing formulas, this can be rearranged to place it in different order. So the speed of light can also be equal to frequency times the wavelength, for example. This is not necessary to remember if you have trouble remembering mathematical formulas, but we will be talking a little bit about the relationships between things like the speed of light and the wavelength of light. Frequency in general, for a particular wavelength, for a particular color of light, the frequency for that color generally stays constant. So as a wavelength moves between different medium, the speed changes and the wavelength will change as well. So we'll talk about that a little bit later. Something, if you do go looking through trying to find information on light, or if you've done a little bit of physics in the past, you may know that there are two competing theories that describe the behavior of particles and of light and energy. So one is referred to as the wave theory and one's referred to as the particle theory. And when we look into the behavior of light, it's very, very, very complex. And one of the quotes that I read recently said that if you think you understand subatomic particle physics, you don't understand it at all. So even those who have, got advanced doctorates in the area, don't understand the actual nature of light. They spend their whole life trying to get more information and more understanding. But light's often quoted as having a strange duality, where the behavior of light can behave either as a wave or as a particle. And when we talk about as a particle, you might think about it as like balls bouncing on the surface, as opposed to waves moving through something like a body of water. They're two very, very different concepts, but essentially both concepts are used to describe different elements and different behavior of light. In gemology, when we're talking about light and when we're trying to understand what's happening within a gemstone when light interacts with a gemstone, we use the wave-like particles of light to help us to understand. And that's because at the larger kind of macro sense, when we look at reflection and refraction of light, the wave theory best describes how light is behaving when it interacts with the gemstone. When we get down to subatomic particle physics, when you start looking at the behavior of individual electrons, then the particle theory describes the behavior of those electrons better than the wave theory. So light has a strange duality, but we're going to be looking at defining some of the elements of the wave theory of light to describe reflection and refraction. In understanding light, we also need to understand waves and how waves move and the wave motion. The way in which light moves as a light wave is similar to how music and sound moves as a light wave and other types of vibrations. And we can also think about it in terms of waves moving through water, through a body of water, or even waves through a crowd of people when we all do the Mexican wave down at the stadium. And we make our own wave that moves through the people. So waves are like little mini vibrations. We might be able to see those vibrations if we play a musical instrument like a violin or a guitar, you will see the strings physically vibrate. And what's happening is that although the wave appears to move across the length of the string itself is not moving in the direction of the wave. The string itself moves in a direction that's perpendicular to the way that the wave is moving. So we've got a vibration direction and we've got a direction that the wave is moving in. And here's just a couple of photos. We've got a pebble that's been dropped into a body of water. And when the pebble drops into the water, it causes the ripples through the water. It causes the displacement of the water molecules. And similar to strings on a guitar, the water molecules are forced to bounce up and down, and that causes the illusion of a wave that is moving away from the particle that's actually in a direction perpendicular to the direction of movement of the water particles. With music, with the guitar, when we pluck a guitar string, the guitar string is forced to move in an up and down movement, but the actual wave appears to move across the direction of the string. So the vibration direction of the string is in one direction, and the direction that the wave is moving is perpendicular to that direction. And that's a very important principle to understand about how waves move through a medium. The medium being the material through which the wave is moving. So whether the wave is moving through air or through water. And when we start looking at a gemstone, it's going to be the gemstone. That's the medium that the light waves are moving through. There's a quote from Leonardo da Vinci when he was trying to explain waves as a concept. He discussed it in terms of water, waves in water, or waves that move through a field of grain. So he says the impetus is much quicker than the water, for it often happens that the wave flees the place of creation while the water does not. So the water is not physically moving away from where the pebble struck the water, but that the displacement of the water molecules is forced to go in an up and down motion. Like waves made in a field of grain by the wind, where we see the waves running across the field while the grain remains in place. In a field of grain, it's easier to understand that the plants are tied to the earth. They're kind of physically stuck inside the soil. So although we see a wave move across the surface, the individual plants can only move in a direction from side to side. Similar when we're doing the Mexican wave, individual people are only standing up and down, but the wave appears to move through the crowd. So basic information about waves. There's some terminology that we can use to understand the wave formation and how we're going to draw a wave and describe a wave. Firstly, waves are repetitious. So they have the displacement of the particles that will go in a positive and negative direction. And that displacement doesn't just happen once, but it occurs repetitively. So the wave function appears to continue on theoretically indefinitely. So waves are repetitious. There's a basic pattern that is repeated, and that basic pattern kind of looks like the outline that the guitar string follows when it's being plucked. The terms that we use, or the concepts that we use to define the wave, we've already discussed when we looked at the formula that can be used to define a wave function. So we've got frequency and we've got speed. We'll have wavelength, And we've also got the amplitude of the wave function. So 3 physical characteristics which are important in characterizing waves is the frequency, the amplitude, and the speed. And then we've also got the wavelength as well. Additional words that I'm going to be using are crests and troughs. And these are points on the wave formation in which the direction of travel of the particle changes direction. Some more definitions for us. Wavelength is the minimum distance between 2 points on a wave that are behaving identically. It's measured in nanometers, 1 nanometer being 10 to the minus 9 meters. And it's also given a mathematical symbol, which is based on the Greek alphabet, and the symbol that we use is lambda. And it looks a little bit like an upside down letter Y. We've got wave frequency. The frequency is the time it takes for the pattern to repeat itself. So if we've got a little counter and we're counting how fast the wave is moving past us, how many crests past that point in any one given unit of time is the hertz. The wave frequency, how fast the wave is moving. And we've got wave amplitude. Wave amplitude is the height of the wave, or the maximum displacement of the particle. The wave amplitude, when we're considering light, the wave amplitude is directly related to the sense of how bright the light is, or how bright the color is. We've got very, very high amplitude. The signal is a lot stronger. If we've got a much lower amplitude, it's very, very weak and we're going to have trouble seeing it. So amplitude, the maximum displacement of a particle, and this is from the neutral position. So the maximum displacement in either the positive or the negative direction. This is a basic representation of a basic wave formation, and this is showing one cycle or one unit before it starts to repeat again. So one wavelength is represented here. We've got the maximum displacement is the amplitude, which is letter A, and we can see that we've got a midline where the wave function is above and the wave function is below. That amplitude is going to be equal in both directions. So it doesn't matter whether we measure the displacement in the upper direction or the lower direction, they're going to be the same. So the amplitude is the maximum displacement in either the positive or the negative direction. The wavelength, see this little symbol down below, that's like an upside letter Y. This symbol here is lambda, and that represents the wavelength of the function, which is measured in nanometers. Now, the definition says that the wavelength is the distance between any 2 points that are behaving identically on that wave function. And what we mean by identically is that here at the origin, where the y-axis crosses the x-axis, at the origin here, the wave function, which is the green line, is heading in the positive direction. It does cross the x-axis midway, but it's heading in the opposite direction. So the particle at the midpoint and at the start, the particles are not acting identically because they're heading in opposite directions. But once it returns back up to where it crosses the x-axis for the second time, then the particles are acting in identical ways. They're both heading in the opposite direction and they're both at an identical position in the wave formation, being the place in which it crosses the x-axis. So the distance between here is lambda. But if we drew this function so that the pattern repeated itself, then the distance between the 2 points where it crosses on the x-axis where the function's both increasing, that length is identical to if we measured it between the 2 crests, which is at the uppermost part of the function, or if we measured it from the 2 troughs. So the 2 crests, the maximum displacement, the maximum amplitude, and the point at which the displacement, the direction of the wave function changes direction and starts to go back down again. So that's the wavelength. A couple more definitions for words that I'm going to be using during this lecture. We have a ray. A ray of light is the straight line path followed by the light moving from one point to another. And unless light interacts with another object with a different optical density, then the light will continue to move in a straight line direction. So if I turn on a torch here and shine it out the door, the light travels in a straight line direction, and we call that a ray of light. A beam is a group of light waves following along the same path. So ray is like a single line of light, beam is a group, and a medium is any substance through which the light travels. So we can be defining the medium as we start going through tonight's lecture and we start looking at reflection and refraction. The medium may be air. The light initially is traveling through air because it comes from the light source, travels through the air, and then comes into contact with the gemstone. Once it enters into the gemstone, the medium changes, and now the light is traveling through the gemstone material. When we're cleaning the gemstone and we're observing a gemstone for evidence of it being a composite stone, when we're looking for the GTD and we've got it in the water, the medium is the water. And when the stone's in the water, the reflections from the surface of the stone are going to be reduced, which is why it's easier for us to see that the crown is red when they're immersed in that liquid. So there'll be different times where we need to define the mediums in which the stone is in or through which the light is traveling in, especially to understand some of the diagrams that we might be drawing. Now, one way of looking at light and how it behaves and trying to understand the pattern that a light wave makes is by considering the movement of slinkies. Who here remembers slinkies? Yay! So slinkies are a really good way to visualize different types of waves. There are 2 main types of waves, or 2 different types of waves that we can illustrate with a slinky. We've got a transverse wave and a longitudinal wave. The transverse wave is caused when the wave and when the particles of the medium are forced to move in a direction perpendicular to the direction that the wave is traveling. So light is a form of transverse wave. And these are just some definitions for you. Longitudinal waves are a little bit different. The motion of the particle occurs parallel to the motion that the wave is actually going in. So it kind of pulses along rather than travels in a perpendicular direction. And I've got a couple of YouTube videos here with some music, which is great. I don't want notifications from YouTube. So showing a slinky, we can see the movement of the wave function, the direction that the wave is traveling in, and the direction of the vibration of the individual sections of the slinky. And the slinky is moving in an up and down motion along the screen, and then the wave is traveling in a direction that is perpendicular to the motion that the hand is making the slinky move in. So this is an example of the transverse wave. And just to illustrate the differences between the transverse wave, I'm going to close all these down so that I don't get myself confused. I have got it. Okay, that's good. The longitudinal wave, and now it's going to make me do a skip. No thanks. It won't let me go to a larger screen, but that's okay. So the longitudinal wave is when the direction of vibration is parallel in the same direction as the direction of the wave, and it forces little pulses along the same direction. So this is not what light is. Light is a transverse wave function. Okay, I'm going to close that down, and hopefully I don't accidentally close down the presentation also. Okay, how's everyone feeling so far? Okay. Now we're going to look a little bit more at the spectrum of white light, or the visible spectrum. The visible spectrum, or the spectrum, is a word that was coined by Sir Isaac Newton when he did some groundbreaking work to establish what the visible spectrum was, and he did this when he was 24. By using a series of prisms, he was able to show that white light was actually a combination of all of the colors of the visible spectrum, and that these colors separated as they moved through the prism and caused a rainbow to appear on the opposite wall. So when the light came through the window, he forced it to go through the prism, it went onto the opposite wall and created a little rainbow. He was able to prove that those colors could be recombined into a single beam of white light by using a second prism to recombine all those colors. So he did this when he was 24. He recognized that white light was only a source of energy, and that the energy had the ability to stir up a sensation of color within our brain through our eyes. So we've got an eye-brain combination that is interacting with the energy that is around us. He also noted that when two different colors are combined, they produce a third single color. And this is what, in one respect, makes light a little bit different to music, because light, when the two different light rays combine, that third color, it's no longer possible to see what the two individual or how many colors have gone in to combine. So if we combine yellow light and blue light, we get green light. And when we look at the color green, our eyes can't distinguish how much yellow or how much blue might be present. However, in an orchestra, where you've got multiple instruments that are playing, our eyes can pick up the vibrations from each individual instrument, even when they're combined into a piece of music. Our ears can still distinguish individual vibrations. But with light energy, when those vibrations are combined, they create a unique third color and a single color. He did this work in 1672, and as I said, the experiments that he did were using prisms to disperse the light. And what we're going to be talking about at the end of tonight's lecture is looking at the dispersion of light and learning a little bit more about how light refracts as it moves through a prism, and what causes the separation of that white light into individual colors of that rainbow. The 7 principal colors, which were defined as red, orange, yellow, green, blue, indigo, and violet, were arbitrarily decided by Newton. So there's many other color variations in between the 400 to 700 nanometers. 400 nanometers is always right down in the deep violet. 700 nanometers is always up at the red end of the spectrum. And each individual nanometer from 400 to 700 actually represents a unique color that is just slightly different from the nanometer either side. And all of these colors graduate and slowly change from one to the other along that spectrum. So blue light has a shorter wavelength and red light has a longer wavelength. So the larger the number, the longer the wavelength. And remembering that the wavelength is the measurement between 2 points on a wave function that are behaving identically. So the further apart those two troughs are, or those two crests, the longer that wavelength is. So let's apply all of these kind of definitions and understanding, and let's look at what happens when light interacts with objects around us. So when light is incident upon the surface, I'm choosing to use the word incident here because it occurs frequently in some of the texts that we might read with we're trying to understand light. So incident upon the surface. Also think back to when we were doing things like the microscope and different types of lighting that we have. We've got transmitted light that comes from beneath the gemstone and travels through the gemstone. We have incident light that comes from above the gemstone and reflects off the surface. So when light is incident upon the surface, it means that we have a beam of light that's traveling in a straight line direction, and it continues traveling in a straight line until it comes in contact with the gemstone. And at the point at which it comes in contact with the gemstone, or the point at which it is incident on the surface of the gemstone, the light may do one of a number of things. Initially, some of the light may be scattered on the surface of the gemstone, and to scatter the light means that it bounces off in different directions, not necessarily following any particular law. If the surface is a little bit uneven, then we might find that more light is scattered from the surface. Most of the light, however, is going to obey laws of reflection or refraction. Light may be reflected off the surface of the material. Depending upon the type of material that we're looking at, depending upon which gemstone, the amount of reflection may vary from maybe 5% to maybe 15% or a little bit more. And the amount of reflection from the surface is also dependent upon the angle that the light makes with the surface. Often the amount of light reflected from the surface, or the maximum amount of light reflected from the surface, is defined as being when the light is traveling perpendicular to the surface. So things like quartz may only reflect 5% of the light back. Things as gemstones such as diamond, I think, reflects about 17% of the light back. So it's a small amount of the light that is incident upon the surface will be reflected from the surface. The light might be refracted as it moves from the air, changes medium, and enters into the gemstone. And as it enters into the gemstone is optically dense. It has more atoms within its structure, and that slows down the speed of light as it enters into the gemstone. So refraction is essentially a process via which the speed of the light slows down. And another thing that could happen is the light could be absorbed by the gemstone. So if a gemstone is fully transparent, the light will enter the gemstone, travel through the gemstone, and come out the other side of the gemstone, or be reflected change direction, come out on a different facet. If a material is fully opaque, then the light is being absorbed by the gemstone and not allowed to travel through. Another example is materials that are black and opaque absorb all of the light that is in contact with them. And that's the same regardless of what materials we're talking about, including things like fabric, which is why black materials are so hot to wear, because the black is absorbing all of that energy, whereas white materials reflect back so much light, so they're reflecting the energy away and not absorbing the energy. So the light can be absorbed by the stone also. In a couple of weeks, we'll start looking at how gemstones acquire colour. And one of the ways in which they are coloured is by selectively absorbing individual colours or ranges of colours from white light. So it could absorb all of the light or just little isolated patches of light. What we're going to be talking about tonight, though, is the reflecting and the refracted light. We'll leave the absorbance of light for another night. So the way in which light is reflected is governed by the law of reflection. And this is a very simple, straightforward little law to learn. And very, very easy. The angle of incidence is equal to the angle of reflection. This also comes up with a number of words that will need to be defined. So we've got the angle of incidence and the angle of reflection, which we'll look at on a couple of slides' time. Now, the reflection is technically a change in direction of the wave front, such that the light wave remains within the same medium and remains at the same speed. So there's no change of speed and there is no change of medium. So if we have a light that is traveling from the lights in the ceiling, it's traveling in a straight direction and it comes down and starts to bounce around or bounce off my sapphire and my ring. As it reflects off the surface, it hits the stone, it bounces off the stone. So the light ray changes direction. It was traveling in a downward direction and then it's going to bounce off in a different direction. So it changes direction, but it stays within the air. And because it's within that same medium, because it's still traveling in air, the light doesn't change speed. So the reflection of light is a change of direction of a wave front at an interface between different media. Interface between different media just means a surface. So we've got air and gemstone, and the surface of the gemstone is the interface between the two different media, meaning the air and the gemstone. And then the wave front, or the ray of light, is going to return to the same medium from which it originated, so back in the air. This is a simple diagram that illustrates the law of reflection. This is using something like a mirror. We've got this labeled as a mirror, but we have a flat surface. We've got a ray of light, and in this case, the ray of light is indicated by a red line. Ah, yes. Yes, no, I know that. I got stuck with that Tuesday last week. I got to the train station. I went,
Thanks.
see ya. Okay, so the law of reflection. The ray of light is indicated by the red straight line. And then the direction that the light is traveling in is indicated by these arrows. So on the left-hand side of this diagram, we have a ray of light indicated by a red line that is coming somewhere from the top left-hand corner of this picture. and it's traveling in a straight line until it meets the surface of the mirror. When it meets the surface of the mirror, we say that it is incident upon the surface of the mirror. And the surface of the mirror is also the interface between the air and the mirror. At that point that the light hits the surface, we're going to draw in an imaginary line that is at 90 degrees or perpendicular to the surface of the mirror. And this imaginary line helps us to define the elements of the reflection of light so that we can define what is happening. And we call this imaginary line the normal. Now, the law of reflection says that the angle of incidence is equal to the angle of reflection. So the angle of incidence is this angle that is made between the reflected ray and the normal. And this is shaded in red, and we've given it a little letter, the small I, meaning that it's incident. So the angle of incidence. And then at the point in which the light hits the mirror, the reflected portion of that light changes direction. So it's no longer traveling in a straight direction. It changes direction, the light bounces off the mirror, and we can now see that there's a second red line with an arrow indicating that the light is now moving to the upper right-hand corner. And the angle of reflection is indicated by the blue portion and the letter R in small case. And the angle of reflection is equal to the angle of incidence. And our rule can be written as I equals R. Now, other notation that we can say, the incident ray can also be called I for incidence, maybe a capital I. The reflected ray might be called R for reflected, and with a capital R, so that we can tell the difference between what's the angle of reflection and what's the actual reflected ray. So that's the law of reflection. So the normal is an imaginary line that is drawn at right angles to the surface at the point at which the light hits the surface. And the angle between the incident ray and the normal is equal to the angle between the reflected ray and the normal. And just to note here that the angle between the surface and the incident, or the surface and the reflected rays, are not quoted, but we can easily work that out. If we are told what the angle of incidence is, because it's measured between the incident ray and the normal is perpendicular to the surface, that means it's a 90-degree angle. If we know what the incident angle of incidence is, we just do 90 minus the angle of incidence, and that's going to give us the angle between the incident ray and the reflecting surface. That might help you with one of the questions in the tutorial when we come to light. Put in the back of your head. Other nomenclature, wherever we can get rid of words and use single letters, it declutters the pictures, which makes them easier to read. So sometimes we will use a single letter rather than a full word. The point at which the ray is incident on the surface is usually also denoted by the letter O for origin. Other nomenclature, we can even label or name the angles depending upon all the elements that are in play. So the angle of incidence can also be named ION, meaning that it's the incident ray and the origin and the normal that are at play. So by labeling all these diagrams, I follow I down to O and follow O up to N, creates a triangle whose angle at the point here at the O is the angle of incidence. So this angle of incidence is labelled by ION. The angle of reflection could also be labelled as NOR.
And what was the F or something?
That's for refraction. So we're going to get to that in a little minute. So this is for light that has entered into the different media. Okay, I've got a couple of YouTube videos here. Again, it's going to force me to do another ad. Skip the ad. Okay. Okay, so can we see, I'm going to just stop this here. So we've got light that's coming from the left-hand side of the screen, and we have a rectangle of glass. Now this is actually showing a couple of things. Remember I said that the amount of light reflected from the surface might only be 5 or 10%, and the higher the refractive index, the more light is reflected from the surface. This comes back to our definition of luster, where luster is the amount and the nature of light reflected from the surface. Gemstones such as diamond have a higher refractive index and reflect more light from the surface, so the surface is brighter, and it's called adamantine luster. Now, diamond, if the light is traveling perpendicular to the surface, diamond will reflect 17% of that light back. So here, the rest of the light is going to enter the gemstone or be scattered on the surface or be absorbed by the gemstone. So what this video here is showing is we have a beam of light from the left-hand side of the screen. That beam of light is traveling in a straight line direction until it hits the surface of the glass block. At the surface of the glass block, we have a combination of reflection of light from the surface of the gem, and we have refraction of light as it enters into that glass block. We've got 100% of the light intensity traveling through air initially. Some of that light is reflected and some of that light is refracted. So the light intensity that is reflected is not as bright as the initial ray of light that was traveling through air, because some of that energy has been diverted to travel through the stone. If I was to draw in an imaginary line at this point here that is perpendicular to the surface, then we can measure the angle of incidence and the angle of refraction, and those two angles are equal so long as we look at the surface of what is happening perpendicular to the original surface. So as I hit play, see how it's showing this reflected ray? Now if I pull it back here, see as he's moving across the surface, the light, the position at which the light hits the surface was changing. So get out of that one and I'll go back to the other one that I had. So this one is refraction. I'll get back to that one in a minute. Okay, refraction. How about I go back to this? Okay, so refraction of light. We'll look at this video shortly first with no sound. And I'll describe a little bit what is happening during this video. Okay, so we've got a hemisphere of glass. Now, because it's a hemisphere of glass, we haven't got opposite parallel faces, but we have a curved face. That's going to help us a little bit in being able to understand the direction the light is traveling. But everything that happens at this straight edge on this little prism of light. The way that he's setting it up, notice also he's got some measurements written on here. He goes from 0, 10 degrees, 20 degrees, 30, 40, 50, 60, 70, 80, and then 90 is back parallel with the x-axis. This little square here indicates that it's a right angle. So this is perpendicular. He's also got the angles written on the lower right-hand quadrant, left-hand quadrant. Don't know my left from my rights. So 10, 20, 30, 40, 50, 60, 70, 80, 90. Now what he's going to do is change the angle of incidence and see how it changes the refracted angle. So starting off with the light perpendicular. When the light is perpendicular to the surface, it's going to travel in a straight line. So the light comes out on the opposite side of this semicircle, parallel to the y-axis, in line with what says 0 degrees. So it's just traveling in a straight line. Now, as he changes the angle slightly, I'm going to let him change it a little bit more than 5 degrees so that we can really see the effect. And here, we've got an angle of incidence that is at 10 degrees. If we trace this ray of light back to where we've got the measurement here, so 10 degrees, but the light changes direction and it's coming out more at about 6 or 7 degrees away from the normal. So this is illustrating refraction of light. Refraction is a little bit more complicated than reflection because the change in the angle is not equal. The angle of incidence is not going to be equal to the angle of refraction. If we continue going, I'll let him get to maybe 20 degrees. See, at 20 degrees incidence, the refracted ray is about 13 degrees. So we have an angle of incidence that is always greater than the angle of refraction. So this is because the light slows down as it changes medium and goes into a more optically dense medium. And as it slows down, it's going to change direction. Refraction of light is defined as a change in direction of the wavefront as it moves between two different media because of a change of speed. Reflection of light is a change of direction of wavefront while staying in the same media with no change of speed. I'm going to head on back to the PowerPoint. So light that is incident upon the surface of the gemstone, not all of it is going to be reflected. The vast majority is actually going to be refracted into the gemstone, or it's going to be forced to travel through the gemstone. So the light that is refracted, that is actually going to travel at a different speed because it is traveling in a different media. And this is a diagram that demonstrates what we just saw in that video. A little bit different to the previous diagram, and in this case the light is traveling, coming towards the gemstone from the opposite side of the gemstone, which could make it look a little bit different again, but there's some similarities. We have a surface. This time, instead of being a mirror, we've got the surface of a gemstone. We've got a ray of light that is traveling in air, and we can see that the direction of travel of the light in air is towards the surface of the gemstone. It keeps traveling in a straight line until it hits the surface of the gemstone, and at that point of incidence, we're going to draw in an imaginary line that is at right angles to the surface of the gemstone. And this is called our optical normal, or just our normal for short. Then at that point of incidence, the light that is refracted into the gemstone changes direction. and it actually appears to bend towards the normal so that the angle of refraction is a lot smaller than the angle of incidence. And this is true when a ray of light enters a material that is more optically dense than what it was first traveling in. So air is considered an optically rarer medium. Anytime light enters any medium that is denser than air, it's going to slow down. And that's because of the chemical nature of the material that it's interacting with. Chemical nature meaning the types of atoms that are making up that material that the light is now traveling through, and the electrical nature of those atoms. So how many protons, how many electrons, and the arrangement of those electrons. And this is all going to slow down the ray of light. So light being part of the electromagnetic spectrum, the electromagnetic interacts with the light interacts with the electrons within those atoms. And it's kind of like if you've got a crowded room and you're trying at a party and you're trying to get from one side of the room to the other, the more people that are packed in that room, if you're trying to get from one side to the other, the more people you need to try to move around. So it's going to take a lot less time than if the room was totally empty. You could run in a straight line very easily. So optical density is a concept via which we kind of measure how slow the light will be, depending on how many atoms the light has to move around. As the light slows down, it changes direction, or at that point of incidence, it's going to change direction. And this is called the angle of refraction. So when light enters a gemstone, it will always be bent towards the normal if the light was originating in air. And usually when we're talking about refraction, we are viewing the gemstone, and we live on Earth where the atmosphere is air. So the light is always traveling through air and then interacting with the gemstone. And when the light enters the gemstone is more dense or optically denser. So the light is going to change direction and appear to bend towards the normal. Refraction is the change in direction of a wave due to the change in speed. And optical density, gemstone is more optically dense than air. Then when light enters a more optically dense medium, the light slows down and the ray changes direction and will be refracted towards the norm. I've said all of that previously. Okay, the more optically dense the medium, the more the light will bend towards the norm as it travels through the stone. So the more optically dense the medium, the slower the light travels. And each individual gemstone is made up of different types of atoms in a different crystal lattice with different spatial arrangements and symmetry between those atoms. So each individual gemstone is going to have a different impact on the light that travels through it. So some gemstones will cause light to slow down a lot, and some gemstones won't have as dramatic effect on light. So the more optically dense the medium is, the more it'll slow down the passage of light. And the speed is also related to the refractive index of the medium. So the higher the refractive index is, the higher the optical density and the slower the light travels as it travels through the material. And this is because more optically dense mediums, more optically dense the medium, the more it slows down the speed. Yeah, okay, because it's got more atoms, or the arrangement of the atoms is different in how the light has to try to travel through the material. The greater the optical density, the higher the refractive index of the gemstone. So diamonds with a refractive index of 2.42 have a much greater effect on reducing the speed of light. They're more optically dense. Quartz, on the other hand, has a refractive index of about 1.54 from memory. So the speed of light through quartz is a lot faster than the speed of light through diamond. In 1621, a Dutch scientist named Willebrord Snellius, which we just refer to as Snell, derived mathematically the relationship between the angle of incidence and the angle of refraction for any two media. We refer to Snell's law of reflection and Snell's law of refraction. Although Snell wasn't necessarily the first person to document these cases, he did publish papers and has been considered the person who gives his name to these laws. Anyway, so going back to the law of refraction, for any two given media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for one wavelength of light. Now, in this definition, does anyone recognize the word sine? Excellent. A few people and a few people at home, hopefully. We don't actually need to be able to define what sine is, and we're not going to be calculating sine of any angle. If you want to deep dive into the mathematics, that is something you can do in your personal time, but it's not going to be part of this course. But Adele,
we actually have an email that we send out debunking trigonometry.
Which,
So I'll get David to send that out.
yes. So Adele is a maths teacher. And if anyone wants to be taught trigonometry, Adele will go through the principles. In the past, we have had students want to revise or know what these things are. If you're a little bit intimidated by the maths and don't want to approach it, that is fine. But Adele does have an email that she's happy to send out explaining what these concepts are. But sine relates to a branch of mathematics called trigonometry, which is all based on right-angled triangles and calculating angles in right-angled triangles given the lengths of the sides. So sine is one of the ratios that can be calculated from a right-angled triangle. So Snell's law of refraction says that the sine of the angle of incidence is related to the sine of the angle of refraction, but that the angle of refraction is not going to stay constant for each individual wavelength of light. And that's really, really important because this is where we get dispersion of light from. Each individual color has a different wavelength, and each wavelength is refracted to a lesser or greater degree. So the ratio is only constant for one wavelength of light only. There's another part to this definition which is also appropriate to reflection, and that's we can draw this concept and this rule. When we draw it on a flat piece of paper in 2 dimensions. And when we draw it on a flat piece of paper, the incident ray, the refracted ray, and the normal are all lying flat on that piece of paper. So the incident ray, the refracted ray, and the normal all lie on the one plane, the plane referring to essentially a flat object or that flat piece of paper. The same with reflection. The incident ray, the reflected ray, the point of origin, and the normal all lie on the one plane, which means we can draw a 2-dimensional picture of that behavior of the light. So here's this diagram again of refraction. And we've drawn in here a couple of dotted lines so that we can see the right angled triangle that is produced by the incident ray and the normal. The right angled triangle actually happens here at the letter A, where we have a straight line perpendicular to the normal that then intersects the incident ray. So we can also look at the size of the right angled triangle from the refracted ray. This right angled triangle is a different size to the right angled triangle made by the incident ray, and the angles are different. So Snell found that the angle of incidence, as he varied the angle of incidence, the angle of refraction varied, but that it varied for the same proportion as he increased that angle. So that's what that video that we started off with was showing. As we changed the angle of incidence, the angle of refraction was changing, but it was changing proportionately to the angle of incidence. And Snell was able to prove that the difference between these two angles were proportional to the sine of the two angles. And sine is a term from trigonometry, calculated based on the lengths of a right-angled triangle. But we're not going to do any trigonometry calculations in this course for those who have not done maths in high school. It's only a requirement that we understand the concepts of the behaviour of light. When we come to look at the refractometer, we're going to come back to this concept of refraction and look at how that's used to calculate the refractive index of the materials. So the amount of light that is refracted varies according to the wavelength of the light, because the rule says that the ratio is constant for one wavelength of light only. As the wavelength of the light becomes shorter, so we go from the red light through to the blue light and we shorten the wavelength, the amount that the light is refracted becomes greater. So in other words, blue light is refracted through a larger angle than red light. And this is the basis for where we get the dispersion of light, where we have one ray of white light, the white light being comprised of all of the colours of the visible spectrum. And as it enters into a material that is optically denser, all of those individual colours are refracted, but to different amounts. And the blue light is going to be refracted or bent to a much larger extent than the red colours, which are not going to be refracted as much. So we get all of those the colours of the visible spectrum get fanned out, and the further that they're forced to travel, the further fanned out they become. Which is why when we used a prism for the light to enter through the prism, on the opposite wall, we get really nice, pretty rainbow colours. If we bring that wall right in close next to the prism, we're not going to get as much of a fanning out of those colours. How are we feeling at this point?
My brain hurts.
Oh,
I don't get it. That's the second time.
Can you get in early on a Monday?
sorry.
Yeah, I can. Before 5:20. So I have,
Contact clinic.
yeah.
Can I reflect this off?
Oh, I thought you were going to change the time on it.
So
Someone should.
it should have a mirror somewhere in my. Does this reflect?
Yeah.
Trying to bend. So the reflection of light, if I shine a light like this laser at a surface, oh, there we go. Can we see on the wall up there? So I'm shining it at the phone. but it's reflecting off the phone and bouncing towards the wall. So reflection of light is we have a beam of light, in this case a red laser. It is traveling in a straight line direction from where the energy output of the laser towards the phone. The phone is a flat surface that is partially reflective, and the light, when it reaches the surface of the phone, changes direction, bounces off the phone and travels in a different direction. When we bounce that light off the surface of the phone, there it is on the wall again, at this phone, if we draw an imaginary line that is perpendicular to the surface of the phone, so at right angles to the phone, and if we were to measure the angle perpendicular to the phone to the beam of light from the laser, that angle is the angle of incidence. The reflected light bounces off the phone, creating an angle the opposite side of the normal that is identical in magnitude or size to the incident ray. So it bounces off in a very symmetrical way. Same way as billiards balls bounce off when you're playing snooker or billiards. So you've got your cue, you hit your ball, and the ball travels in a straight direction. If you've hit it true in the center, travels in a straight direction along a straight line, and then it bounces off the edge of the table. And that edge of the table is going to cause the ball to bounce off in a different direction. The direction that it bounces off follows the same laws of reflection that the light follows also. So if you were to draw in an imaginary line right angle, then the angles between the incidence and the reflection is going to be the same. So you can predict when you're playing snooker where the ball is hopefully going to go if you've got your measurements right. Hopefully, if you've got the measurements right. I'm really, really bad at playing snooker. So I either never hit it hard enough or I don't get the angles right and it doesn't go where I want it to go. But in my head, I'm tracing it out going, ball's going to go there, then it's going to go there, it's going to go straight in that pocket, and it never happens. Reflection, the light, instead of bouncing off the surface, some of the light, if this phone was transparent, some of the light enters the phone. And when it enters through and travels through the phone, it changes direction because the speed forces it to slow down. It's actually in a PowerPoint from 2 weeks, in 2 weeks' time. I should probably pull it up to now. We talk about a wave front. The wave front is actually the combination of all of the rays of light that are traveling together. They all have like different curves on their wave function. If we think about a wave front being that combination of wavelengths or individual waves as a four-wheel drive car, if we're driving at an angle and we go from road and off-road into a piece of sand or dirt, the wheels are going to sink down into the dirt and slow down a lot quicker. If both wheels hit the dirt at the same time, then the whole car slows down at the same time and we don't change direction. So that's what was happening in that video when the light was coming in perpendicular to the surface and it was exiting that hemisphere at 0 degrees, parallel to that y-axis. The light was slowing down, but we couldn't see the effects of it. As we change the angle of the light that is incident, it's like that truck is traveling at an angle and just one wheel hits the dirt. When it's traveling along and one wheel hits the dirt, that wheel slows down suddenly and the other wheel is still moving a lot faster. So the truck changes direction. So it's forced to swing around the wheel that slows down first. So that's what's happening with refraction. we've got this wave of light, and one side of the wave is forced to slow down faster than the other side, and the whole thing kind of swings around and changes direction because of the change in speed. Does that make sense? Yeah? Okay, so we're going to take what we know about reflection and refraction, and we're going to start talking about something called total internal reflection of light. And this is what's happening when light is already inside a gemstone, how the light might behave depending upon the angle that it's traveling or the direction that it's traveling in. For us to understand total internal reflection of light, we want to consider not those light rays that are traveling through air in a rarer medium, but we want to consider what's happening to the light inside the gemstone. So it's already entered the gemstone, it's in the denser medium, and we want to consider what happens when that light is interacting with the surface of the interface of the medium between stone and air, but going from dense to rarer rather than rare to dense. So this diagram represents this concept of total internal reflection. And we're going to introduce a new term, which is critical angle. The critical angle is specific to individuals, species of gemstones, and it's related to the refractive index of the gemstone material. The critical angle, which here is the stronger dotted line, which is I1, represents the critical angle of the gemstone material in this diagram. The critical angle is an angle of incidence that a light ray makes with the inside surface of a gemstone that forces the light to be refracted at 90 degrees in the less dense medium. So if this is gemstone and air, then light that is already inside the gemstone may hit the inside surface of the gemstone, and if it makes just the right angle, that light is going to exit the gemstone but just scoot across the surface of the gemstone. So in this case, we're looking at light that is interacting with the table, and light that follows the path of the critical angle ends up refracted in air and just scooting across the surface of the table of the gemstone. And that will travel in a straight line direction forever and ever and ever until it hits another object, in which it'll either reflect or refract and do all of those things. Now, with total internal reflection, the behavior of the light depends upon the angle that that light makes with the surface of the gemstone. If the angle of incidence is greater than the critical angle, then all of this light will be totally internally reflected within the gemstone, and that light will obey the rules of reflection, so that the angle of incidence equals the angle of reflection. And all of that light just changes direction, stays in the same medium within the gemstone, and just continues to bounce along. So it changes direction until it reaches another surface, and then it may change direction or exit the stone. Any light that makes an angle of incidence that is less than the critical angle is going to be refracted into the less dense medium. And because we're going from a rarer medium, a denser medium to a less dense medium into a rarer medium, then the speed of light is going to speed up when it enters the air. So the change in direction of the ray of light is going to be away from the normal. It moves towards the normal when the speed of light slows down. It moves away from the normal when the speed of light speeds up. So this, in a nutshell, describes total internal reflection of light. Why do we need to know about total internal reflection of light?
Diamonds.
Diamonds. Yes. All
Faceting the gemstone.
faceting a gemstone. All gemstones are faceted to optimize their optical performance. One of the characteristics or one of the principles of optical performance is the brilliance of the gemstone. And the brilliance comes from the amount of light that is reflected back from the pavilion facets. So when we look in through the table of a gemstone, we want the gemstone to be reflecting back light to our eyes. So the gemstone acts as a little hall of mirrors. It captures the light that enters in the crown, it reflects it in the pavilion, and it returns it back to our eyes. If it doesn't reflect any light back to our eyes, then it's essentially the same as a pane of window glass. The pane of window glass that we look out in the windows into the street is essentially a gemstone material. We can facet glass, we call it paste, but if it has two parallel surfaces, then we look straight through it and there's minimal reflection back. So it doesn't have that brilliance effect and it doesn't sparkle. We need those facets to be at the right angle to reflect back that light. And the angle that the facets need to be at is larger than the critical angle, because this critical angle is the difference, or where it's kind of very finely balanced between the light that is reflected and the light that is refracted. And any light that is refracted from inside the gemstone leaves the gemstone into the air. So total internal reflection. Another application of total internal reflection, fiber optic glass. So principles on how fiber optic glass work and things like telecommunication is they have these long strands of glass and a laser, and if they angle the light from the laser just right, it keeps reflecting along the line of the glass. But it needs to be reflecting along the critical angle or just outside, larger than the critical angle, to keep bouncing along. So the angle needs to be just right. And there are other applications of total internal reflection if you look it up also. Okay, so let's have a look at another YouTube video. Okay, this is basically the same YouTube video. Basically the same. So we've got this hemisphere again, and notice here, even though this is curved on the dome, if you take the surface as a series of tiny little flat surfaces, then what we have here is a tiny little flat surface that is parallel to the larger flat surface on the other side. So if we take a tangent at this point, or a flat line that is perpendicular to where the light is interacting, and the tangent is parallel to that opposite flat surface. As the light enters in the dome here, it's going to be traveling parallel to this line, which is the y-axis. It's going to exit out the other side, and you can see it's still parallel to that line and following 0. So 0 degrees to 0 degrees. Now we're going to change the angle slightly. So changing the angle of incidence. We can see here that we've gone 10-degree angle of incidence, and the light is traveling through the glass. You can see the bright point on the opposite face at which the light is incident with that surface. And now we're looking at what's happening on the inside surface of the glass. So the inside surface of the glass, and all of the light is essentially exiting the glass, and it is refracting. Now it's actually 5 degrees here, not 10, because that's 10. So we've gone 5 degrees and it's refracting away. It's actually at about 7 degrees out here. So we've gone from a dense material to a rarer material, and the refraction is larger. It's bending away. Now we'll go up to 10 degrees. So 10 degrees, and now it's refracting out of the glass at about 13 degrees. So the angle of refraction is larger than the angle of incidence. And this is because we're considering light that is inside a material that is optically dense and looking at what happens when it leaves that material into a medium that is optically rare. Okay, so we're approaching 20 degrees angle of incidence. And at 20 degrees angle of incidence, we've got an angle of refraction that's about 32, 33 degrees. And so far, we've still got refraction happening. At some point, though, it's going to be a little bit different, and I'm going to let it go until it finds the critical angle. Have a look. Oh, no, when I say let it go, what I want you to concentrate on is this refracted ray at the above the glass hemisphere. And just look at this behavior. At some point, it's going to snap down to 90 degrees. And I'm going to pause it again when it snaps down to 90 degrees to the normal. Oh, at this point here, notice that we're getting just a small amount of reflection.
There's a rainbow.
And there's a rainbow. Look at the dispersion. Okay, now that I just missed it just a little bit. Let's just put it back just a little bit. There. So here we've got maximum amount of dispersion, and it's approaching 90 degrees. And we've kind of lost it a little bit, but we've still got just a little bit of rainbow across there. This here is the critical angle. The critical angle is the angle of incidence in the more dense material that causes an angle of refraction in the less dense material that is equal to 90 degrees. So the light is essentially scooting across the surface of the flat part of the hemisphere. But as we approach the critical angle, we're starting to get a small amount of internal reflection within this hemisphere. And you can see that the angle of incidence here is the same size as the angle of reflection. So we've got a change in direction of wave front remaining within the same material, and there's going to be no change in speed because it's remaining within the glass, and the angle of incidence is equal to the angle of reflection. Now,
Oh, sorry.
when I go for it,
Is that
Kathy?
90 degrees only? We watched it.
No, so we were wanting to capture the moment at which the light that is refracted outside the material is refracted at 90 degrees to the normal. So that's refracted in air. As we go past the critical angle and we keep increasing the angle of incidence, look at what's happening to the reflected angle. So the angle of incidence keeps on increasing. The reflected angle also increases, but keeps pace with the incident angle of incidence. They're the same size, so the overall angle keeps getting larger and larger and larger. But you'll notice now that all of the light is being reflected at that point. There's no light that is exiting the glass. It's all being reflected. So this is total internal reflection. Total internal reflection means 100% of the energy of that light is being reflected, and that only happens at specific angles. It only happens when the angle of incidence is larger than the critical angle for the material. So as he increases the angle of incidence, the reflected angle is also increasing because we have that law of reflection. And if we go right back to the beginning here, and play from here. When we start off, because the angle of incidence is less than the critical angle, when we start off, we have no reflected ray and all of the light is being refracted. So small angle of incidence means all of the light is refracted into the air. Then we get to a point of the critical angle where we have an angle of incidence that equals 90 degrees. And then after that, all of the light is being internally reflected within the hemisphere. So this is just showing total internal reflection of light. Okay. So we're going to go through this again point by point. So property of gemstones is total internal reflection. And it happens because we're not dealing with a geometric shape that only has parallel edges, but we're dealing with interesting shapes with lots of facets where all of the facets are at different angles. We're also not viewing the gemstone in a static environment, but the gemstone's position to the light and our eye's position to the gemstone is always changing. And so the interaction of the gemstone with the light will always be changing also. So we have total internal reflection. And what we want the gemstone to do is most of the pavilion facets of the gemstone, we want them to scoop up and capture as much of the light that enters through the crown, whether it's through the table or through the facets at the side of the gemstone. All of the light that enters the gemstone, we want it to reflect internally and then come back out through the crown of the gemstone to our eye. And that's going to increase the sense of the brightness of the gemstone. And total internal reflection considers a special situation where the light has already entered the gemstone and then how that light interacts with the surfaces, but the inside surfaces of the gemstone, whether it's going to be reflected or whether it's going to be refracted into the air. So this is another picture that is showing total internal reflection of light, but dealing with a container containing a liquid and then a red laser. And if you get the angle just right, and if the angle is larger than the critical angle, then none of that red light from the laser escapes the surface of the water, but all of the red light is reflected within that body of the water. So to define or discuss total internal reflection, we want to consider only those rays that are already within the gemstone and looking at what happens when those rays hit the surface of the gemstone at the division between air and gemstone. What's going to happen to those rays? And to illustrate it, we're going to consider three possibilities. One possibility is the ray of light makes an angle of incidence that is less than the critical angle, and all of those rays get refracted out of the gemstone material. One possibility is the angle of incidence is going to equal the critical angle, and the critical angle is defined as the point at which the ray of light refracts out of the material into the less dense media, but makes an angle of refraction at 90 degrees to the medium. And then the third illustration is any ray of light that makes an angle of incidence that is greater than the critical angle is totally internally reflected within the gemstone material. And I think I said all of those. We sometimes write critical angle as CA, which is just an abbreviation of critical and angle. And sometimes I might accidentally write that incorrectly and be CI, which confuses everyone. And every year I swear I'm going to fix it, and every year I don't. So CA is the correct abbreviation. The critical angle is the angle of incidence of a ray in the denser material, which is refracted at 90 degrees in the less dense material. And when we say refracted at 90 degrees, we're measuring that from that imaginary line called the normal. And the normal itself is at 90 degrees to the medium. So if we're looking at a gemstone, when it's refracted at 90 degrees, that light is just scooting across the surface of that facet. These are two other screenshots also using hemisphere. Yes.
Could you just pop that for one quick second?
Yes.
Thank you, sorry.
Okay, so the hemispheres, using the hemispheres again and lasers. If the angle of incidence is greater than the critical angle, then the light's going to be internally reflected. And if the angle of incidence, just wait, it's coming from the top left-hand corner and totally internally reflected. But if the angle of incidence is greater than the critical angle, depending upon the actual angle, most of it will be refracted. We may have a little bit of it reflected when it is close to the critical angle. The critical angle being the angle of incidence at which it is refracted at 90 degrees. So the light would actually be coming down this direction if it was at the critical angle. Okay, so light is making an angle of incidence that is equal to the critical angle. We kind of consider it to do two things at the same time. We consider it to scoot across the surface of the stone and be refracted into the less dense medium. But when we come to discuss the refractometer in a couple of weeks' time, it also helps our understanding of the use of the refractometer if we also consider that to be the point at which total internal reflection occurs. It's only a fraction of a degree, a couple of minutes, either side of that critical angle at which reflection or refraction may happen. So it suits our understanding to also define the critical angle at the point at which total internal reflection is going to happen. Light rays making an angle of incidence that's less than the critical angle are refracted out of the gemstone. And because it is going from a more dense to a less dense, they get refracted away from the normal. And light rays making an angle of incidence that's larger than the critical angle are going to be totally internally reflected within the gemstone. And here's another couple of diagrams that are just slightly different, but exactly the same as previous. Okay, and another diagram. I'm going to skip past this one. Okay, now I'm going to skip over that one. Okay, a little bit of maths. I mentioned earlier that the critical angle is related to the refractive index of the gemstone material, and there is a mathematical formula that relates the two. So sine of the critical angle is equal to 1 divided by the refractive index of the gemstone, when sine of 90 degrees equals 1. So sine of the critical angle being the point at which the light is refracted at 90 degrees to the normal, equals 1 divided by the refractive index. So therefore, as the refractive index increases, the critical angle decreases. So they move in opposite directions. So this helps us in a way to try to understand the behavior of light within gemstones, depending upon what the refractive index of the gemstone is. So generally speaking, the smaller the critical angle, the brighter the gemstone is going to be. Also remembering that anything that is captured between the critical angle and the normal is going to be refracted out of the gemstone. If we have a very small critical angle, that gives a lot wider area for allowing for total internal reflection of light, which is why gemstones with a small critical angle are much brighter, because a lot more light is being captured and reflected inside.
What does it mean by 26 minutes?
26 minutes is a fraction of a degree. So a degree is divided into 60 segments. So 26 minutes is almost half a degree. So critical angle of a diamond is 24 degrees and a little bit, 26 minutes. The refractive index of diamond is 2.42. The refractive index is critical angle equals 1 divided by the refractive index, and we can transpose that to calculate the refractive index from the critical angle. And the critical angle of quartz is 40 degrees, so the refractive index of quartz is 1.54. Now let's look at faceting very, very briefly. And this is a little bit of an application of this total internal reflection of light. So gemstones are faceted to optimize their optical properties. And we want brilliance, we want dispersion, and we want scintillation. And all of these are different properties of optical performance of the stone. Brilliance is the total amount of light that is reflected back to the eye. Dispersion is how much of the white light is broken up into the component colors of the visible spectrum. And scintillation is this phenomena that gives us this kind of twinkly effect in gemstones. When you look at a gemstone, not all of the facets of the pavilion are reflecting back the same amount of light at the same angle. Some facets are very, very bright, and some facets are not so bright because the angles are different, and the amount of total internal reflection depends on the angle that the light makes with the facet. So we change the angle of the facet, or we change the angle that we're looking at the stone, the intensity of the light that is reflected is going to change. And because we have a pattern of facets with many facets in the pavilion of the stone, not all of those facets are going to be bright at the same time. So scintillation is the pattern of light and dark that changes as we tilt the stone from side to side. So the way in which we view the stone changes that pattern of light and dark. And that kind of adds to the sense of the sparkle.
It's not really sparkly, but in opal, is that anything like that?
Different,
Colour.
different in opal. In opal, we've got constructive and destructive interference. And we'll get onto that in 2 weeks' time with optics. So internal brilliance is achieved with the help of total internal reflection. And scintillation is that each individual facet, because of the different angles, is reflecting different amount of light with regard to our eye. And then as we tilt it, we change the amount of light that's reflected. So if we have a look at what is happening with the critical angle and how much light is reflected internally, these blue cones trace out the critical angle of the material. So the critical angle being the angle measured between the normal at which the light is refracted out of the gemstone material. Any angle of incidence that is larger than the critical angle is totally internally reflected. And we want as much light as possible to remain within the gemstone. So if the angles of the pavilion are cut correctly, light that enters in through the crown, it refracts, so it changes direction and, oops, I pressed the wrong button, changes direction and continues in a straight line path until it comes to another interface between two different media, between gemstone and air. And at that point, depending upon whether the angle of incidence is greater than the critical angle or less than the critical angle, that light will either reflect internally or refract outside of the gemstone. If the angle of incidence is greater than the critical angle, then it's going to be totally internally reflected, change direction, stay within the gemstone and travel in a straight line direction until it hits another interface between gemstone and air. If the angles of the cutting are correct, then at this point, the light is also going to make an angle of incidence that is greater than the critical angle, so it falls outside this cone of brilliance, and the light changes direction, stays within the gemstone, and now heads up to the table. At this point at the table, the light makes an angle of incidence with the table that is less than the critical angle, so it falls within this cone of brilliance, and at that point, it's going to refract out into the air. So this is a well-cut stone and well-performing stone. This cone of brilliance, when we said the smaller the critical angle, the more bright the material is. If the critical angle is very small, then this blue cone is very, very small, which means there's a large amount of space for all of the light to be totally internally reflected. If the critical angle is very, very large, then this blue cone is very, very large, and there's just a small amount of area for light to make the right angle to be totally internally reflected, but a lot of it is going to be refracted out. So there's not as much intensity of light remaining in the stone, so it's not as bright. The more light that remains in the stone and comes back through the table, the brighter the stone is going to be. So stones with a higher refractive index are naturally more bright. So the critical angle is very important to faceting of a gemstone. If the gemstone is cut too deep, then total internal reflection happens at the first point of incidence, and then it travels across to the opposite side of the pavilion, and then it refracts out. And that creates a stone that looks dark under the table and has too much extinction. We call that an extinction characteristic. If the gemstone is cut too shallow, then all of the light that makes that first contact with the pavilion facet gets refracted out and actually leaves the gemstone through the pavilion. And that's what we call a window. There's not a lot of light being reflected back, so it's not very brilliant. So when we've got a dark stone, we refer to this as a fisheye. That's because it's over deep. So this is an example of a fisheye. The light comes in through the crown. It travels in a straight line direction after it's refracted into the stone, travels in a straight line direction, makes an angle of incidence that's larger than the critical angle, is totally internally reflected, but now makes an angle of incidence at point B that is less than the critical angle, and the light exits the pavilion. If the gemstone is too shallow, then most of the light is going to refract at point A. So this picture here shows a shallow gemstone. The light enters the table, is refracted into the gemstone, travels in a straight line direction to point A, makes an angle of incidence that's less than the critical angle, that's supposed to be inside the red cone, and then is refracted out. And this has a very big impact on the performance of a gemstone, whether the gemstone reflects light or doesn't. So I've got two different gemstones here. One is correctly cut with the angles on the pavilion, and when looking through the table, you cannot read through the gemstone. The gemstone material is actually transparent, but because of the angles that the stone is cut with on the pavilion, so much light is being reflected back that we can't actually see out of the gemstone. That's on the left-hand side. On the right-hand side, we have a stone that is very shallow, and because it's very shallow, the light just travels straight through the material. It refracts a little bit and changes direction of travel, but it essentially enters the table, exits the pavilion, and therefore we can read through the material. And this stone doesn't perform very well. It's not going to be very bright and it's not going to give any sparkle. It's going to be fairly dead, like a piece of window glass, which is why we call it a window effect. When we turn both of these materials upside down, we are changing the angles. The table is now at a different angle to what the pavilion was from our viewing direction. And we can see that both materials are in fact transparent. We can read through both of those materials when we lay them table down. So critical angle and faceting, as the refractive index of the gemstone increases, the critical angle of the gemstone material decreases. And this has an influence on what angles are used during the cutting process. So stones with a higher refractive index will be cut slightly shallower to stones with a lower refractive index. So when we're comparing something like diamond to something like quartz, quartz is naturally going to be a lot deeper in the pavilion to get the same optical performance. So for diamond, we want the refractive, the pavilion angles to be between 37 and 40 degrees. But for quartz, we want the angles to be about 43 degrees. So a lot deeper angles for quartz, which makes a lot deeper gemstone. If we cut quartz with exactly the same proportion and angles on the pavilion facets as diamond, then we'd end up with an overly dark fish-eyed quartz. So we need to cut appropriately for the refractive index of the material. I'm going to skip through all those. And dispersion of light, we're going to finish on with next week before we start refractive index. Has anyone got any questions? Excellent. Where did we get up to? Which slide number? 76. Okay. That's okay. We've got about 10 slides before next week. Then we go on to refractive index.
More fun. More science.
Were there any questions online?